Great. Ooh, that's loud. Sorry. All right. So our next speaker is Wonyeol Lee. He's going to be giving a talk on smoothness analysis for probabilistic programs with applications to optimized variational inference.
Okay, thank you for the introduction. I am Wonyeol, a final year PhD student at Stanford, and this is a joint work with Xavier and Hongseok. So I'm going to present our paper on smoothness analysis for probabilistic programs. But I will spend most of my time on the first part about smoothness analysis, although this is a probabilistic inference session. So before I start, I'd like to make a clarification, which is in this talk, the term smoothness will mean any kinds of property of functions describing well-behavedness, such as differentiability or Lipschitz continuity. Okay, then, given such definition, why should we even care about such smoothness properties at the first place? So to explain this, suppose that we are given a probabilistic model, then we can apply many different inference algorithms. But if we know that this model is differentiable, then we can apply more efficient algorithms, such as pathwise gradient estimator. Similarly, if a neural network is Lipschitz continuous, then we can do many interesting things, such as proving robustness guarantees or so. And actually, there are many more examples where knowing the smoothness properties can be very useful. So in a sense, it is quite important to find out the smoothness properties, especially automatically and soundly. But we all know that these objects of our interest are all expressed by programs. So our actual goal would be to find out such smoothness properties of programs. So in this talk, I will explain how we can achieve this goal. But to do so, we need some basic definitions. So for concreteness, I will focus on the differentiability of the deterministic and imperative programs. And as an example, consider this function, program P, which stores the exponential of x to y and the sign of x to z. And I will assume that all those variables are real valued. Then it is quite clear to see that the semantics of P can be given as a function from R3 to R3. And I will define the differentiability property of P in the following way. So we say that in program P, y is differentiable in x if the following condition holds, which is, so first, since we are looking at differentiability in x, we fix the values of all variables other than x, and then consider the semantics function of P. And since we are looking at differentiability of y, we focus on the x part of the input and y part of the output of the semantics function. Then we can get some function f from R to R. And if that function R is differentiable in the standard mathematical sense, we say that in this program P, y is differentiable in x. So easy definition. So under this definition, you can easily check that in this program, y is differentiable in x, but z is not differentiable in x, and so on. And these are the kinds of properties that we want to find out. But what we figured out in this work is that it is surprisingly subtle to find out such smoothness properties, especially automatically, soundly, and precisely enough at the same time. So from now on, I will explain why this is the case. And to do so, suppose that we want to compute the differentiability of a program, especially in a compositional way. Then one challenging case for such analysis is as follows. So given two programs P and P prime and two sets of variables U and V, we want to check whether the input variables U are differentiable in, output variables U are differentiable in input variables V in the composed program P semicolon P prime. So this is the property we want to check. And one way to do so is to use this kind of reasoning rule based on the chain rule. So what this rule says is that if we can deduce the conclusion of the rule if we can find some set of intermediate variables t such that each output variable u is differentiable in each intermediate variable t in the second program, and a similar thing holds for each input variable v. So given this rule, we can easily see that this rule looks quite sound based on the chain rule. And although this rule looks pretty simple, this rule or its variant was actually proposed and studied in Pyro. Okay, so these are pretty good, but let's be more careful about the soundness of this rule, whether this rule is indeed sound or not. And to answer that question, consider these two programs P and P prime, which assign sign of x to y and x plus y to z. And also consider z as the output variable and x as the input and intermediate variable. Then you can easily see that for this case, the two premises of the rule are satisfied, mainly because x and x plus y are differentiable functions of x. It's easy, but you can see that the conclusion of the rule is not satisfied. And this is because the output variable z becomes x plus sine x after executing p and p prime. And this function is non-differentiable in x. And this example basically shows that this rule is unsound. But this is a bit weird because it looks sound and based on the chain rule, but it is unsound. So let's figure out why this is unsound. So to do so, let's revisit this example. And if you see this example and these premises of the rule, you can see that we actually check the differentiability between some variables in P and P prime, but we don't do that for some other, the differentiability between some other important variables. So for instance, in the second program, z depends on y, and in the first program, y is non-differentiable in x. So because of this, in the entire program, z is non-differentiable in x. But this rule does not check such problematic dependency and non-differentiability, and this is the reason why this rule is unsound. Okay, so here is one lesson we can learn from here, from this example, which is we need to consider dependencies between variables in order to do sound reasoning about differentiability. Okay, so given this unsoundness, we can try to fix it by considering all possible dependencies between input variables and output variables. In other words, we now check the differentiability between each output variable u and all intermediate variables t, which is the whole variable set. And we check the same thing for each input variable v. So this is a fixed rule. And after making that fix, the second premise of the rule does not hold anymore because sine is not a differentiable function. So this means that we cannot deduce the conclusion of the rule. And this implies that this rule is sound at least for this particular example. And actually, this rule looks pretty sound for all other cases because we are now considering all possible dependencies between input and output variables. Okay, so it seems we are done now. But actually, there is yet another important problem. So consider the differentiability between the same variable x before and after the two programs p and p prime. Since these two programs does not change the value of x at all, x is clearly differentiable in x in the entire program, right? But the second premise of the rule does not hold again by the same reason as we saw before. So we cannot deduce this very simple differentiability property if we use this particular rule. So in other words, this rule is very imprecise to be used in practice. Okay, so this is the second issue, but for now, let's just admit this imprecision of the rule and revisit the soundness question, whether this rule is indeed sound or not, even though it looks sound. Actually, I showed you that it is unsound. So let's consider these two another programs, P and P prime, where we assign x to y and f of x, y to f. F of x, y to z, sorry. And also consider z as the output variable and x as the input variable. Then we can easily see that the two premises of the rule are satisfied, mainly because this function f is a partially differentiable function, meaning that it is differentiable in each of its arguments. Okay, But the conclusion of the rule is not satisfied because the output variable z is a discontinuous function of x if we run the whole program. So this basically means that this rule is unsound, even though we made some fix to the previous rule. So yeah, this is a bit weird because we think this was sound. And let's find why this is unsound by revisiting this example. And here is the reason. So this rule, the premises of the rule, actually check that these two functions shown in this slide are partially differentiable. They do check this, but here is an important property of partial differentiability, which is this property is not preserved under function composition. And because of this, this output variable z is non-differentiable in x in the entire program. And so the conclusion of the rule is not satisfied. So in short, this rule is unsound mainly because it implicitly assumes some property of differentiability, but that property is actually invalid. Okay, so from here we can learn another important lesson, which is we need to identify and check the assumptions on the target smoothness properties that are made implicitly for soundness. Okay, so to summarize up to this point, the main message here is that it is very subtle to do smoothness analysis soundly and precisely. Given this, I'm going to present our approach to smoothness analysis and how we handle such subtleties. Okay, so first in our approach, we consider smoothness properties between sets of variables, not between individual variables. And we also consider kind of arbitrary smoothness properties parameterized by phi, which denotes any set of functions that we consider smooth as smooth. So for instance, the differentiability property we have considered so far corresponds to phi equals all partially differentiable functions. Actually, we can use another phi, such as all jointly differentiable functions and so on. And we define, after fixing this particular phi, we define phi smoothness of a program in a similar way that we defined the differentiability of a program earlier. So we say, for example, we say that in P, xyz is phi smooth in yz if the following holds. First, since we look at the different smoothness in yz, we fix the value of x in the input and consider the semantics function. And since we consider the different smoothness of xyz, we focus on the yz part of the input and xyz part of the output, as we did before. Then we get some function f from R2 to R3. And if that function is contained in the set phi, then we say that in this program P, xyz is phi smooth in in yz. Okay, so these are the kinds of properties we want to find. And actually, we do find such property by computing two functions, dp and sp. Here, dp denotes kind of stores the dependency information of p, and sp stores smoothness information of p. And each of these functions map a set of variables to another set of variables. And they should satisfy this invariance. Namely, for any set of variables v, this dp of v should be the set of all variables on which v may depend. And this sp of v should be the set of some variables in which v must be phi smooth. Okay, so these are the invariants. And given this, we can compute the function f in a pretty standard way, inductively. And so I will just skip this rule. But the rule for the s function is quite non-trivial. And let's try to understand this by considering which u is inside this SOV set. So by the definition, u is inside this SOV if and only if it is contained in both of the sets in the right-hand side. And this first inclusion means that this can be a bit tricky. It means that if we consider all variables on which v may depend in the second program, then those variables must be smooth in U in the first program. And the second inclusion means that if we consider all variables in which V may be non-smooth in second program, then those variables must not depend on U in the first program. Because this can be a bit confusing, but essentially speaking, the right-hand side describes the conditions under which we can safely apply the chain rule. Okay, this is how our analysis works. And actually, there are many more details in the analysis, but you can find it in our paper where you can ask questions. And one of our main results is that our analysis for phi smoothness is actually sound if the target property phi satisfies 5 assumptions. And here are some assumptions. So the first assumption is that the composition of phi smooth functions should be phi smooth. And the second assumption is the same should hold for the pairing functions, pairing and so on. And this table shows various smoothness properties and whether each of them satisfy each of these assumptions. And you can see that the partial differentiability property does not satisfy the composition assumption. And actually, this makes our analysis unsound for this case. But if we consider joint differentiability, then it satisfies all the assumptions, so our analysis becomes sound for this case. Actually, there are many more smoothness properties that satisfy all these assumptions, so we can apply our analysis for any of them in a sound way. Okay, so this is about our smoothness analysis and concludes the first part. And I will very briefly talk about how we can apply this to variational inference, how to optimize variational inference. So at a high level, variational inference is essentially a minimization problem about two probability densities, P and Q theta. And here the function L is the function we want to minimize. And in practice, we typically minimize this function by using the gradient descent algorithm. But this particular gradient is generally difficult to compute because this function L is defined as an expectation of some another function. So what we do in practice usually is to just estimate this gradient, not compute it exactly. And there are two popular ways to compute this gradient, basic estimator and optimized estimator. So this estimator works as follows. So we first sample some value z, and then compute some quantity about z and the gradient, and then return the computed value as an estimate of the final desired gradient of L. Here, details are not important. Important thing is that we have to compute gradients in the right-hand side. So both of these estimators require some differentiability requirements, such as Q theta should be differentiable in theta, and so on. You don't need to know the details. Important thing is optimized estimator requires more than the basic estimator. And because of this, in practice, we apply the optimized estimator selectively only to some of random variable zi. And in order to do so soundly, we need to know which parts of the density functions are differentiable. And these density functions are usually expressed by programs, so we need to be able to find out the differentiability of a program. So here is the part where the part one comes in. So we apply this approach of soundly optimizing gradient estimators to probabilistic models written in Pyro. And we counted the number of random variables to which the optimized estimator was applied. And also we counted the same number of random variables, but optimized by Pyro's default optimizer. And here I would like to note that our approach checks the differentiability requirements using our smoothness analysis, so it is always sound. But Pyro's default optimizer does not check those requirements, so it can be unsound in some cases. And here are the main results. So the one in the blue means that our approach optimizes one random variable in a sound way. But the two ones in the red means that Pyro optimizes two random variables, but one of them is optimized unsoundly. And you can see that our approaches rediscovers all of the sound optimizations that Pyro makes, but with soundness guarantees. But Pyro makes some unsound optimizations in 2 cases, and we found that those unsoundness are due to branching or division by 0. And because of this unsoundness, Pyro's default optimizer performs worse than ours. These are our main results. And I'd like to conclude with 2 high-level messages. So first, it is very subtle to do smoothness analysis in a sound, automatic, and precise way. And second, there are some PL research opportunities for machine learning, like ours, where we propose setting analysis and use it to automatically plan the inference algorithms. And that's it. Thank you for your attention.
All right, thank you very much. We have time for some questions. Does anyone have any questions? Yeah. Please introduce yourself.
Hello. Great talk, by the way. Very accessible.
Could you speak up, please? Yeah.
Yeah. Okay. It was a great talk, very accessible. Loved it. I'm Purva. I'm from UCLA. I'm a PhD student there. So I was curious if you have any future work in mind with respect to using these analysis properties for HMC algorithm in STAN.
Yeah, that is a very good question. We may be able to apply our smoothness analysis to kind of wisely and soundly apply HMC, because HMC requires also the differentiability requirement. So there is a good future work. We don't plan to do that, but if you are interested, we can talk more. I mean, yeah, good approach, yeah.
Any other questions? Yeah.
Hi, I'm Eric. I'm a PhD student at MIT. So this may be a little off topic, but I was really curious how you discovered that Pyro had this bug.
Yeah, actually, this bug is quite old. So we discovered, so this is a kind of report, kind of issue in GitHub. This was reported like 2020. We met Fritz at POPL'23, but we discovered this earlier than this POPL one. Actually, we discovered this one when we work on kind of inference for non-differentiable models for kind of another old paper. And we actually used Pyro to see how well it works. And actually, we found that it is biased, it is incorrect. So yeah, there we, like 2018 or so, we found bug. We finally know how to fix that bug. Yeah.
Hi, Wonyeol. Thanks for the great talk. I'm Alex, also at MIT. You mentioned your 2018 paper. I know that in this paper you were looking at choosing between sort of reinforce and reparameterization trick at each choice. But do you think this gives you a way to automatically choose when to apply your estimator from 2018?
Yeah, that is a very good question. So our 2018 paper, New Waves paper, is about kind of extending the pathwise gradient estimator with correction terms so that we can apply it for non-differentiable case as well. So basically, we can apply that estimator in any non-differentiable cases, but there was some assumptions like affine thing. So maybe we can do some, so I don't think this work directly applies to those cases because that estimator is applicable to non-differentiable case, but we can do some more analysis so that we can kind of estimate the variance of that estimator and this estimator and choose between them. I don't know, but there can be some places. Yeah, we can talk later. Yeah.
Hey, everyone in the back. Sorry, we had some technical difficulties and went a little bit over. If you guys could just wait 3 minutes before conversations start, that would be great. Thanks. Excuse me, in the back. Please quiet down a little. We're not done yet. Thank you. I had a question. So this smoothness analysis, combining it with variational inference is really interesting. And I'm kind of curious, were you able to establish using your analysis that certain programs are smooth and then, extend the class of models that you're able to apply variational inference to? I'm curious if that extra precision you got in your analysis bought you some more programs that you could run.
Could you repeat the question?
So I'm curious if by separating the smooth, because a lot of existing methods, they just apply variational inference.
Right.
So you're doing an analysis and determining the degree to which smoothness exists. And I'm
Right.
curious, did that buy you more programs? Were you able to apply inference on more things because of that? Or were you mostly throwing away bad programs? I'm kind of curious if you got any extra ones.
So the point of our work is that we can analyze the smooth parts first and then apply some estimator based on that smooth information. So I don't think our approach can increases the class of programs to which we can apply some method, or I mean, it would be kind of opposite way because we kind of restrict the class of programs to which we can apply certain estimator, but in a sound way. So I would say our approach increases the soundness of the current methods, not increasing the class of programs to inference algorithm. Yeah.
One more question.
Hi, I'm Purva again. It is a follow-up question on Stephen's question, actually. So, okay, so as you said that you weren't able to find newer programs that for which you can use the variational inference, but were there any interesting programs that you actually rejected that, okay, these are actually not smooth, which you thought were smooth, and you realize that variational inference cannot be used there?
Oh, could you repeat the question? The last part.
Were there any programs that you found that were that did not have this smoothness property that everybody thought was smooth and rejected variational inference as an inference algorithm for those programs?
Oh, so are you asking whether we could find some program which is not smooth, and because of that variational inference kind of breaks down? Is that oh, okay? So actually we don't have any practical example for that. So this so this first example is kind of a toy example. So it is not a very practical example. The last one, the second one is AIR, which is a very large program. So it is indeed non-differentiable, but actually in practice it works somewhat well. And that the non-differentiability is due to division by zero error. So it can have some effect on the biasness or unbiasedness of the estimator. So we haven't checked whether that estimator is biased because of this non-differentiability. That is the first thing we can do. And also, we can also try that if we fix that bug, then can you get better performance for this model? But yeah, I like to repeat that for this particular model, it works pretty well in practice. But you may be able to make it better by fixing this bug. Yeah.
Great. All right. Well, let's thank Wonyeol one more time.
Thank you.